Yes, hello everyone. Welcome to the Agentic AI Frontier seminar today. It's my great pleasure to introduce our speaker today, Alane Suhr from UC Berkeley, ECS. And Alane Suhr is an assistant professor at UC Berkeley, ECS, affiliated with Berkeley AI Research Lab. Alane's work focuses on building language using systems that communicate with and learn from human users in collaborative, situated interactions. Prior to joining Berkeley, Alane completed a PhD in computer science at Cornell University, Cornell Tech, and spent a year afterwards as a young investigator at the Allen Institute of AI. And floor will be yours, Alane.
Great. Yeah, thank you so much. Cool. Okay, so today I wanted to talk about some research we've been doing at Berkeley on training language-based agents. So first I want to talk about what I mean by language agents. So an agent, in my definition, is an entity that takes actions that influence the state of some system in which that agent is embodied. So you could imagine like a game, like situated 3D game, and then the agent is taking actions, moving around, modifying things in the world. A language using agent is one that includes natural language in its input and output space, which means that the agent isn't just taking actions in the world, it's also generating natural language and also taking as input natural language that like other agents are producing. And this is a little bit distinguished from a language-based agent, which is what a lot of people are working on today, which are agents that are built on some kind of language technology, like an LLM. So taking as input maybe some high-level task specification, but really relying on the information learned in the LLM to help it reason about what actions it should take in a domain. So there's a number of different tasks we've studied for language agents. One is collaborative instruction following, where we have a couple of agents in an environment, and they are working together towards a shared goal. And the one of the agents is giving instructions to the other one towards that shared goal. Another popular approach or task these days is automated software engineering, where an agent takes as input some kind of natural language description of like a GitHub issue, and then maps this to a sequence of actions that modify the current state of a repo. So instead of directly generating the patch or pull request, so the newest version of the code that we want to update, the model itself is actually generating actions that modify the code. So edit actions or execution actions where maybe it's testing the code. So think about the kinds of actions you take as a software developer. The agent here is taking those actions too. Another popular task nowadays is also language conditioned device control. So you can imagine, browsing the web, maybe you want to buy something, but it's a lot of clicks for you to compare all possible options of the thing you want to buy. So you could instruct the model to say, hey, go through this website, get all of the, I don't know, couches or something like that, and then create a table that compares them in terms of cost and fabric and that sort of thing. And so then the model is actually taking the same kind of actions you would take as a web navigator, clicking on things, entering search terms, and so on. Okay, so this is the task, and we want to build a system that can do these tasks. But this is kind of hard. So a couple of reasons this is hard to do specifically for agentic tasks. Most modern success in language technologies, so think like chatbots like ChatGPT, relies on large-scale pre-training data. So these models are trained because we have access to so much text data on the web of people communicating with each other, which is in another term, decontextualized demonstrations of language use. So imagine, scraping some forum, you have demonstrations of people using language together in a conversation, for example. But if we think about the kind of data that we need to train an agent, we're missing a lot of this data. In particular, we're missing the sort of actions that this agent is going to try to take. So if you consider the task of grounded instruction following, for example, navigation, we don't have demonstrations of the actions that they're actually taking or the observations that this navigation agent would be making. For software engineering, maybe we do have uh, labels in terms of, we can scrape GitHub, we get GitHub issues, and then we get the pull requests that solve those issues, but we don't have demonstrations of the actual underlying process that the software engineer took in order to create the pull request. So that's sort of like a weakly supervised setting where we have the correct pull request, but we don't know how it was created. And then for collaborative multi-turn interactions where more than one agent is communicating with each other back and forth, we do have transcripts of people communicating with each other. For example, think of the sort of forum example, but we don't have examples of people interacting with the agent that is being trained. And this is actually very important for us to learn from, but we don't have access to it, particularly because as users interact with these systems, they're going to adapt to the system's behavior. And we don't know what the system's behavior is until we train it. So we have this sort of chicken and egg problem of we just can't get this data to train from. So even if we did collect a large number of ground truth demonstrations, let's just hire thousands of software engineers and then have them write pull requests and we record the edits they do with their keyboard. This is still actually not sufficient for agent tasks because when we train only on demonstrations, we create brittle models that are prone to error propagation. What I mean by error propagation is these tasks underneath the hood are sequential decision-making tasks where an agent takes an action, updates, that action is executed, it updates the state of the environment, and then the agent has to perceive the new state of the environment. And if the agent makes a mistake in an action, suddenly the observations that it has to process later on might not be the ones that might not be the ones that it was trained on, right? So now we have some out of distribution training observations. My slides are showing up okay, right? Just want to verify.
Yes, yes, we're seeing the slides now.
Okay. Great. Okay, so one solution to this is that we should train online, where during training we don't just look at the actions that like an expert made, conditioned on some observations. We actually learn from the agents themselves generating action sequences and then training on those action sequences. And this is what partially motivates approaches like reinforcement learning from human feedback, where during learning, we're not just learning what are the instructions and continuations that humans created, but also sampling from our language model and then having either a human or another model rate what we sampled from the model. Okay, so some core questions about training language agents that I'm going to talk about today. First, how can we train them without having sufficient demonstrations from human users? So we're going to talk about learning through interaction with human users and learning through interaction with an environment. Another core question is how can we actually evaluate these systems, especially as we're having them complete increasingly complex tasks. So we'll talk about automatic approaches to this. And then third, I'm going to talk about an approach, a new approach that we're exploring more in depth on making these agents more efficient at inference time via parallelization of subtasks and subtask decomposition. Okay, so the first question is how do we learn these systems from interaction with users? And one underlying question that we need to answer here is if we have a system that's interacting with a human user in deployment, are there signals that we can use from that interaction that we can use to improve model performance? So in this setting, we are exploring a system that maps from instructions and observations to action. So this system is following instructions. This is a game that we set up a while back. It's a collaborative instruction following game called Serial Bar. A human is going to be giving instructions to an agent that is moving around in the world. And you can see the observations that this system might be making as it's following an instruction to pick up this card with 3 red stripes. So the core question is, how do we improve this instruction following system by just deploying it with human leaders, humans who are providing instructions? And the main setup we're going to operate under is we're going to get binary feedback from the users as they're observing the instructions being executed, and then we're going to learn from this via casting it as a contextual bandit learning problem. So during this game, a human will issue some instructions, and then the system, the follower, will move around. And the user has the opportunity to give feedback, positive or negative, in real time as the system is moving. So in practice, what this looks like is you have a human give an instruction like move forward and slightly to your right until you see a card with 2 black squares, pick it up. And we have the system executing and sampling and executing some actions from its current policy. And as it's doing this, the human has the opportunity to give positive or negative feedback. So now the system has moved sort of the agent has moved closer to the black squares card, so it's getting some positive feedback. But now maybe it looks like it's going to get this orange star card, so it's going to get some negative feedback. And then it keeps going, getting some feedback, and then finally, once it actually selects the card with 2 black squares, it gets some positive feedback. So during interaction, during a sample, just like you just saw, we have an instruction that's provided to our follower. The follower takes some actions that transition it from world state to world state. In this case, its location in the environment. And for some of those actions, it gets some positive or negative feedback. So for each action that the follower executes, we have access to the state in which it sampled the action. We have access to the instruction given by the human. We have the actual action that was sampled and executed. We have access to the policy's probability of that action. And then we have some optional binary feedback. So I'm not going to go into depth into how we're actually computing the objective here, but at a very high level, the learning setting is we are going to initialize our agent policy using some supervised data. So this is human demonstrations of instruction following. We're going to do this with supervised learning. And then during deployment, we are going to sample actions from our policy, conditioned on instructions provided by humans during deployment. So every time we're learning, we're actually taking a random person, pairing it with our agent. They're going to issue some instructions, it's going to execute some actions, and the people will give it some rewards. And from this, we're going to create a training data set that looks like sets of these actions paired with some other data. And we're going to learn from this with contextual bandit training. And we're going to do this over multiple iterations. Or rounds where we're going to deploy for maybe 300 interactions with users on average. Then we're going to collect the data, update the policy on it, and then deploy it again. So in our main experiment here, we did 11 rounds of learning where we deployed and collected some training data in each round. And we find that over time, the rate at which the system is successfully completing the tasks users ask it for, this is continually increasing. So the policy is actually learning. This is a game. So this is the serial bar game where the agents are incentivized to maximize the score by collecting sets of matching cards. So we also evaluate whether the score is going up, and indeed it is, from 3.5 to 5.3 points. And this is really good because ultimately, the humans they want to use the agent to maximize their score. So learning is supporting that. But one thing that kind of complicates this, because this is a dynamic process where a human is interacting with a system that's also changing, well, the humans also have the ability to change over time. So this is the same population of users that's interacting with this system across 11 rounds. I think it was about 50 people in total on Mechanical Turk. And we see that over time, step by step, across rounds, the users are also adapting. So for example, they simplify their instructions. They don't ask the system to pick up multiple cards per instruction. They just use one card. And so what this is obviously going to be a confounder when we're looking at how the model has improved at following instructions, because the thing changing over time between round 1 and 11 isn't just the model parameters, it's also the set of instructions that we're evaluating here. So one question would be, well, okay, so we're changing the questions. Are the questions getting easier? And does that mean that that's why we see the performance improvement. So what we did to evaluate this is we took the very, very first model, the one that was just pre-trained, no learning from interaction, deployed it at the very end, and we saw there was a significant performance improvement from 66.7 to 70.4% instruction execution accuracy. So yes, the humans adapting and simplifying their instructions did make the system be perceived to perform better. But we also see this gap, between the blue line and the red line, where the blue line is the model parameters that are updated over time. So the model, our learning algorithm is improving the model's performance as well. Okay, so summarizing this, we can continually learn by iteratively updating model parameters through during this sort of rounds of deployment and optimization in interaction with people. We're learning from explicit feedback. In other work, we also looked at implicit feedback, so where people aren't actually, giving binary feedback to the system. And one core takeaway here is that in any learning system like this, we really have to take into account not just how the system's changing, but also how users are adapting to the system. Okay, so a second set of questions here is how can we automate evaluation of these models, especially as we're getting them to execute more and more complex tasks. So here we're looking at the task of digital agents, where our user has this sort of request, tell me the cost of my latest canceled order, and then you can take some agent and maps this to a bunch of different actions, so clicking, entering text, and so on, and then this will then report some answer. You can also think of device control, so a user asks a question to their phone, and the phone navigates and then provides an answer to the user. So this is a super, hot topic. Everybody's interested in this these days. There's been a lot of progress, but these systems aren't perfect. And one of the issues is that as we're deploying them on increasingly complex tasks, we want to be able to evaluate their performance relatively easily. We also maybe could use this evaluation to actually improve the models. So let's talk about digital agent evaluation. In terms of existing benchmarks, there's two main classes. The first are simulation-based benchmarks that provide executable environments, so an actual sort of phone emulator, for example, and user instructions. And each instruction is paired with handcrafted test cases where people write in, these are the states of the environment that you have to reach in order to execute this instruction correctly. So you have environments like Web Shop or Web Arena. There's also demonstration-based benchmarks where the user instructions are paired with expert demonstrations, so expert action sequences, but they don't actually have an executable environment. So the main challenge here is you cannot deploy a model, an arbitrary model in these benchmarks because they don't have an environment that you can execute actions in. So in order to evaluate models using these benchmarks, you have to use reference-based metrics where you look at the sequence of actions that your model would have generated given the demonstration prefixes from the expert demonstrations. So you have data sets like Pixel Help, Android in the Wild, a couple others. Okay, so the key question here is how can we automate these evaluations and go beyond needing the handcrafted test cases, but still having access to an executable environment. So the core question is we want a system that answers, did our agent successfully complete a task? So when this evaluator takes this input, gets some input, it gets an instruction X, and then a trajectory A, the sequence of actions, and S, the sequence of world states. So the screenshots, for example, in this task. And we want our system to tell us this is right or wrong, if it's wrong. So we can think of end-to-end evaluators, which just take these inputs X and A and S and give us, some judgment. You could take some VLM model like GPT-4 that is just prompted to take some image inputs and some text inputs and give an output. Another option is a system that instead modularly processes these inputs. And here, actually, there is a minor error in my slides. The main idea is let me see if I can just quickly. No, I don't think I can change it. So the main issue is in this case, we want to first process the instruction, and we want to independently process the instruction and the trajectory that was sampled. So first, we're going to take just the actions and the states, so just the trajectory, and we will caption it. So you can imagine this like we should only have a line going from A and S to this first pink box. Um, so this is going to be, again, another VLM. It's just trying to say what happened in this trajectory. So we get some text-based caption that tells us what happened. And then we'll take a text-only LM and prompt it with that caption and the instruction X to answer the question of whether the agent successfully completed the task. So by decomposing this problem, we are first understanding what the agent did, and then we're understanding whether what it did was what was specified in the instruction. One of the benefits of these approaches is we can use powerful uh, open source models locally, like QuenVL, to do these two parts separately and still get really good performance for our systems. So I'm just going to try to go through this a little bit quickly, which is we have a couple of options. We have the end-to-end evaluator, we have the module evaluator, and what we want to do is see how well our evaluators match with the metrics that are provided by the the benchmarks that we are interested in across different agents and in different sort of domains like device control or web navigation. And then there's the second question of, can we actually use these evaluators to improve the agent policies? So back to the benchmarks a little bit, we look at Web Arena, which is this sort of web navigation task that has Oracle hand-designed test cases paired with instructions. And then we also have demonstration-based tasks, benchmarks. In our case, we use Android in the Wild, where in order for us to evaluate like the capabilities of new agents, we actually have to go in and write human annotation. We have to look at like, what did our agent do and did it do it correctly? Because we don't have test cases. And in our work, we also explore a new domain of iOS device control. So we explore two core policy, or for the two benchmarks, we look at different policies. So for Web Arena, at the time, the state of the art was a GPT-4 text-only model that took the HTML tree of a web page and turned this into actions. For Android in the Wild, we look at three different policies. The first are the demonstrations provided by the dataset. The second is what was at the time the state of the art, Cog agent, and then we also evaluate another model, Auto UI. In terms of the evaluators we're comparing, first we evaluate this end-to-end model. It's a GPT-4V model. We then have a captioner plus Mixtral modular approach. So the vision language model is an open source model that captions the trajectory. The language model is also an open source model, open weight model, Mixtral. And this allows us to run this evaluation locally, which means it's easier to scale up and see what the models are doing on the inside. We also experiment with replacing the text-only model that reasons about instruction completion with GPT-4. Okay, so the first question is, how well do these evaluators match with the Oracle metrics? So in Web Arena, that's test cases, and in Android in the Wild, that's human judgments. And we see that overall, our evaluators are quite high in accuracy, especially for Android in the Wild, and the best model for that is the captioner. So we have an open source captioner in GPT-4, which is the uh, uh, thing that's deciding whether the system did what was asked. So one aside is the dataset Android in the Wild is a reference-based, provides a reference-based metric called action matching score. And what this metric is telling us is for the gold standard demonstrations, for each of the actions in those demonstrations, what proportion of those actions did a policy predict correctly, given the gold standard prefix of the demonstration. So this is kind of like teacher forcing, where we provide the agent with the gold standard actions so far, and then ask it, what would you do next? And for the state-of-the-art model, we were getting like 70%, 70.7%, and Auto UI, we saw the large version is better than the base version. So one question is, given our evaluators, do we make the same conclusions as this metric? So here I'm showing the success rate that's evaluated by a couple of different evaluators. So first is human judgments. In blue, that's us going in as authors and like annotating the annotating the trajectories. And then we experiment also with three of our evaluators, so GPT-4V, Captioner plus Mixtral, and Captioner plus GPT-4. So three takeaways from this. First, we find that the human judgments of the reference demonstrations, so this is the human policy on the right, these are the gold standard annotations coming from this benchmark, only 64.2% of these are actually successful. So this is not great if we're going to use this benchmark to evaluate because it's going to be wrong a third of the time. Another issue is that we see a different conclusion between whether auto UI base and auto UI large is better or worse. So auto UI base for us actually performs better, even though it's a smaller model using our evaluators, all of our evaluators. And then another thing is we actually find that the numbers we're getting are much farther from the numbers that we're getting from the reference-based metric, which were in like the 70s, 70% accuracy. And so this is telling us that useful digital agents are actually much farther than what these reference-based metrics are telling us. Okay, to summarize this section, we are proposing these autonomous evaluators that take input, which are the traces of an agent that has executed some actions. And next, we're going to look at what else these evaluators could be useful for. So sort of going back to this question of how can we learn through interaction, now how can we learn through interaction with the environment? What kind of signals can we get through execution? So again, we're going to operate under this setting where we have this instruction following setting. A user provides an instruction, the agent has sampled a trajectory, including actions and world states that it's visited. So another way of putting this is this is a Markov decision process. We have states and actions, and then we have a transition function that tells us if I execute an action in some state, what's the next state going to be like? And then our policy, our agent, is telling us which action we should choose given a current state. And we know that expert policies are different from agent policies. So when we're training from human demonstrations, we're going to get error propagation because the agent's going to visit states that we've never seen before during training. And so that is a problem. So we want to learn through execution in the environment so the agent is at least exposed during training to the kinds of observations it's going to make during deployment. So in general, you can describe most of these environments as having states. So in serial bar, it's like the locations of the players on this game board. The actions are turning around, stepping forward and backward. We have a transition function that is implemented by the game itself. And then our ground truth evaluator is the real-time human feedback that people are providing that we learned from in the first section of the talk. For a task like language condition device control, we have states that are like screenshots. We have actions like clicking and scrolling. We have a transition function implemented by a GUI. And then our ground truth evaluator is going to be something like human eval or test cases like in Web Arena. And like we saw in the previous section, we have other evaluators too. We have automated evaluators that maybe we could learn from here. And then let's consider software engineering. So here our states are like the current version of a file, the current working directory, any running processes, and then the action space is like anything you can do in a shell. So executing stuff, running profiling tools, debugging, plus text editing. So actually editing the files we need to edit. And the transition function is just implemented by the shell or the word processor. And our ground truth evaluator here is test cases. So let's say that we're operating in this environment where we're taking issue descriptions in GitHub and we want to create a PR. Well, most of those issues are going to be paired with unit tests in the repo. And so if the proposed PR actually passes all those test cases, then we actually have a good PR, and this tells us we've succeeded. So we don't actually need human supervision. We actually already get it from having scraped GitHub. So one thing to note is that the most popular benchmark for evaluating software engineering is called SWE-bench. So it has like 2,200 tasks. Issues are paired with the gold patches or the gold PRs. The transition function is implemented by having an actual environment, like a virtual environment that you can download. You can execute arbitrary commands. It's already set up to include the dependencies and have the repo already like installed. And that makes it really easy for us to evaluate arbitrary policies, right? Because if we take some arbitrary agent, we can have it execute whatever actions it wants, and we'll still get some states to come out of that. And then it also pairs each of these issues with ground truth executable test cases. So in practice, if you want to eval on SWE-bench, SWE-bench is going to take your system, it's going to sample some actions from it, and then it's going to get some generated pull request from your agent, and we'll test it by executing these test cases. And if it successfully passes all the test cases, your agent has succeeded. So that's great for evaluation, but what if we want to actually train agents for software engineering? One of the issues is that SWE-bench only includes issues and issue descriptions and gold patches and environments for test data. So it doesn't actually have environments for the training data, which means we can't learn by executing actions in our environment. We can only learn from weak supervision we get from the kinds of issue descriptions and gold patches in the training data. So we also have this environment called SWEGEM that we propose for training software engineering agents. This was published at ICML this summer, and it includes, in a similar structure to SWE-bench, a bunch of GitHub issues paired with gold patches, but also paired with environments, executable environments that any agent can go in and execute some tasks. So our training environment has roughly the same size as SWE-bench's test set, and we actually find that the environments in SWEGEM are actually more difficult than SWE-bench's environments. And so this supports development of training algorithms for software engineering. And I think I believe I'm gonna talk about some results we have from actually using SWEGEM to train some software engineering agents. Okay, so there are a couple different ways that we can improve software, just general agents, by using automated evaluation systems. So the first setting we're going to look at is improving agent policies at inference time. So no training involved, just can we get our model to take better actions at inference time? So if a user says something like, tell me the cost of my latest order, we have our agent attempts to do this. If we have an automated evaluator, we could actually detect or estimate whether that attempt was correct or not, right? Because that's what our evaluator is trying to do. So if our evaluator tells us that it's wrong, then we're going to try again, evaluate again. Maybe it's wrong a second time, and then we're going to attempt it a third time. And then maybe at this point, our automated evaluator says, you did it right, and so we can use this as the attempt that we provide the user. And we find that when we train our evaluators that we talked about just in the last section, we can get up to 29% relative improvement for an agent without any training. And this is over its sort of baseline performance. And so here I'm showing for 3 different evaluators, the green, yellow, and red models are our evaluators that we proposed. We also have this sort of skyline performance, upper bound performance improvement in the blue dashed line, and this is using the Oracle evaluator, which are the test cases in WebArena. So we still have a gap. We still have a way to go in order to achieve that. But we still see without any policy training at all that we get good performance improvements using our automated evaluators. Another way to do this at inference time is to re-rank proposed trajectories. So we're going to train automated evaluators again. So I'm going to go a little bit in depth into how we're training those models. So at training time, we have, and this is for software engineering, we have a bunch of issues. So this is like a training set of issues. We get a policy to sample a number of patches, and then we can tell whether those patches pass the test cases or not. And we do this using SWEGEM. So in SWEGEM, we can take our agent, we can sample some trajectories, and then we know whether those patches resulting from the trajectories pass the test cases or not. So then what we can do is just train an automated eval system, an automated model to take those issue descriptions and the trajectories and map those to some probability that the trajectory passes the test cases, just using supervised learning. So now that we've trained our automated evaluator with this kind of data at inference time with a new policy, what we can do is take an issue description from the test set in SWE-bench, we can take our policy, we can sample and trajectories, and then use our trained evaluator to estimate whether or not that would pass the test cases. And for the one that is the most likely to, according to our trained evaluator, that's the one that we're going to actually keep around and propose as the trajectory. So we evaluate this approach in SWE-bench, and we find that, so the green and blue lines here are two different evaluators that we trained, or we're also calling them verifiers, with different sizes. So we have a 32 billion parameter verifier model and a 7B parameter verifier model. We see that as we increase the number of rollouts, the number of samples from a policy, and use our evaluators to re-rank those, we get increasingly improved performance. The upper bound performance here is if we selected any of the patches from that were sampled in order that using the gold standard test cases. So that's peeking into the test case execution in SWE-bench and telling us which, if any, of those are passing the test cases. So again, we still have a way to go because our evaluators here are not consistently ranking the item that will pass the test cases as the best thing to choose. But we are getting significant performance improvement over time. Okay, so we talked about how we can improve our agent policies at inference time. Now, could we actually improve the policies by training them? So if we have access to the policy parameters, this is something we might want to do. So one approach is called filtered behavior cloning, where essentially at training time, we take some task descriptions, we sample them, we evaluate them using either a gold standard or an estimated evaluator to get some labels of positive and negative. And then what we'll do is we'll just throw out the ones that are negative and just fine tune the policy on the ones that were positive. So when we do this with software engineering, we use our evaluators trained. We use SWE-gem to sample some trajectories. The SWE-gem test cases tell us which of these would pass the test cases or not. And we see for evaluation on SWE-bench that if we do multiple iterations of this approach, of sampling from our policy and fine-tuning only on the things that pass the test cases, we get significantly improved performance in terms of the resolve rate, so the rate at which the issues are being resolved correctly. And for a second metric, which is the rate at which the patches that are proposed are empty, meaning that something really went wrong, this is significantly decreasing. So the base policy, I believe this is like a Quen model, at the very beginning, almost 50, like probably about 55% of the time is giving us trajectories that result in like invalid patches. Whereas after we do this training approach, we get that happening like maybe 25% of the time. And when we put together both the filtered behavior cloning of the policy plus the re-ranking using a trained evaluator, we see even better performance improvements, up to 32% resolve rate on SWE-bench verified. And the last approach we can do for training our policies is, instead of using filtered behavior cloning, where we're training the model just using supervised learning on successful trajectories, we're actually treating those evaluator judgments as rewards and using more sophisticated learning algorithms like PPO, for example. So in work last year in NeurIPS, we evaluate or we present this approach called DigiRL, which is an RL-based approach for device control, using a trained evaluator model as a reward function during learning. And what we see is that with DigiRL, which are the yellowish orange lines, we get significantly better learning curves than with filtered behavior cloning, which is the simple version that's just fine-tuning on successful trajectories. Okay, so to summarize this section, we can use automated evaluators to improve performance. These are automated, we don't need any human intervention here. We can do this at inference time with things like reflection or sample and re-rank, or during training by actually optimizing agent policies themselves. And one of the key takeaways here is that we're moving from training with demonstrations to training from off-policy, or sorry, we're moving beyond training from off-policy demonstrations, for example, from human experts, towards training on samples that we're actually getting from our agents at deployment time. And this helps solve some of the problems of error propagation where, for example, the model gets into a state that it's never seen before because it wasn't trained on the policy that's actually deploying. Okay, so now I want to move on to the last section, which is on making these agents more efficient at executing actions through task decomposition. So one question here in general is, we've been talking about these sequential decision-making tasks where, for example, when we're doing software engineering, we have this current state of a repo, we sample and execute some action, like maybe executing some code or editing the code a little bit, and then that gives us a new state of the environment, and we keep going step by step. But you could imagine a software engineering task where you could imagine solving a software engineering task by splitting it up between a couple different people, having someone work on one part, maybe the front end part, having another person work on the back end part simultaneously. Maybe there's a bit of communication between them, but you could parallelize that process. So I want to start questioning this notion of, are our tasks actually sequential? And if they aren't, are there design decisions that we've made that we don't actually have to make? And so this is going to be talking about work that we're going to present at Column next year, or sorry, in the next 2 weeks in Montreal. Okay, so we could consider many of these tasks instead as hierarchical tasks. So if you think about some kind of task input, maybe a math problem specification, there might be multiple paths to get to different solutions, and in between there's some kind of reasoning. So for example, in software engineering, like I just mentioned, maybe there's multiple possible causes of a bug. You could get different engineers to look at those different causes. Maybe we want to refactor all of our files according to some new standard. We don't have to do that like sequence by file by file. We could hypothetically get all of our engineers to each edit one file in parallel. For like a math reasoning task, we might have different strategies to approach a problem that we want to try out that we don't have to do sequentially. Maybe we could work backwards from multiple possible solutions. And in general natural language reasoning, like let's say we're going to do a literature search or try to explain some kind of difficult task, we might want to look at different possible explanations of some phenomenon. Or if we're writing some text, maybe we want to do this hierarchically where we can jointly, write an intro and the method section at the same time. So, I mean, the iClear deadline just passed, and we were definitely doing a lot of that where, I was editing one part, one of my students was editing another part, a collaborator was editing a third part, and we can all do that in parallel. Okay. So when we think about reasoning models, there's a couple of different inference structures that people have proposed. So the simplest one is zero shot, which is just we have some input, we have some question, and then we're like, okay, model, what's the answer? So you imagine some really complex math problem, and then what we want the model to give us is just the answer. And all it's doing is just mapping directly. There's no underlying reasoning. But of course, we know that models work better when we allow them to generate tokens in a sort of reasoning space. So chain of thought is the most famous example of this. We prompt the model to think step by step, and then it produces some latent representation of reasoning that in practice gives us better solutions at the end. A number of approaches propose parallel samples. So for example, in a consensus approach, we might take this task input, sample multiple possible solutions in parallel, and using chain of thought, and then look at the proposed solutions for all of the different chains, and then take like the majority of them, which in this case would be the blue solution. And we might have more complex inference processes like tree of thoughts, debate, inference with verifiers, that sort of thing. For example, maybe we have a bunch of different chains here that we sample in parallel, and then we send all of them to another model that will look at the chains and the answers and propose solutions, and then put this into one solution. So here, maybe the reasoning for the pink solution was really compelling, and so even though blue is the majority, the model's going to end up generating the pink solution. So these are some inference approaches, but we can also train models to be better at reasoning, right? So one approach is off-policy learning, something like S1, where we have a bunch of different problems, we sample some reasoning traces, we get some result, and regardless of whether the solution is right or not, it's useful to fine-tune on these sampled long chains of thought. So S1, I think only maybe 2/3 of the annotations here are actually getting us correct solutions. Regardless, the important part is we're training the models to, similar to the problem we had with like off-policy learning, we're training our models to be exposed to the kinds of states that they will be exposed to when they're doing step-by-step reasoning. We can also do this using reinforcement learning. So we sample a bunch of trajectories, and here we're going to evaluate with a verifier whether those those approaches were those proposed solutions were correct. And then what we're going to do is fine tune on the successful ones, and we're going to keep doing this over and over. So this is also a form of filtered behavior cloning. And what we find when we learn through exploration by sampling from our policy is we can learn new search strategies. So for example, we find for DeepSeek R1, the quote unquote emergence of strategies like aha moments, where essentially what's happening is the model is going down some reasoning path and then quote unquote realizes that that's not going to get the right result. So it goes back, backtracks. And then when maybe we're navigating the tree like this, we end up in some, not good solution. And then eventually we do find the correct thing. And because we're learning through exploration, we can identify these kinds of structured searches over the sort of space of possible solutions and reasoning. But what happens is this is serialized for these models. So this is where we're getting like long chain of thought models. Reinforcement learning is also incentivizing increasingly lengthy reasoning chains. So over time during learning, we see the length of these chains getting increasingly long. And this both stresses the context windows of the model architecture and also increases computational complexity in terms of how much data it has to process. And the problem is inherently hierarchical, right? So we saw just before that this is a hierarchical reasoning process. So what we propose instead is what's called adaptive parallel reasoning, where we're going to, in parallel, explore this reasoning tree. So we train language models to distribute their inference time compute across both parallel and serial operations, which will in turn navigate the reasoning tree both breadth-wise and depth-wise. And there's two key components that we propose. First, we augment the model output space with fork and join operations to fork new processes and then have them join back the parent processes. We also train the system with reinforcement learning to discover optimal inference structures that we wouldn't have seen if we just sampled gold standard demonstrations of success. Okay, so the task that we're looking at here is the countdown task. This is a simple like math reasoning task where we're provided some input integer and then some target integer and then 4 input integers, and we need to find a mathematical expression that combines each of the inputs exactly once to get us the target. So for an approach like stream of search, which was introduced at Column last year, we in this kind of approach, we have the same inputs. And what we'll do is we'll explore this reasoning tree serially. So we will try out different constituents of the arithmetic expression until we find something that might be the wrong answer. Then we'll backtrack and continue the sort of extending the context by trying different expressions. And so from left to right here, this is like what are the tokens that are being introduced into the model context. And eventually, we're going to exhaust the context. And in this case, we might not see the solution because we didn't have enough tokens to find the solution. In our proposed approach instead, adaptive parallel reasoning, what we have is a parent thread. And that parent thread can choose to spawn subthreads. And those subthreads are completely new, like inference on the same language model, conditioned on a unique context that is provided by a parent thread. And really critically, if nothing else to take away from this, the child threads are operating only on the context that's provided by the parent thread, which means that it is reducing the context limits, that it's reducing this stress on context limits, and it's also filtering the information flow. So the child doesn't have to reason about the high level task, it only has to reason about the task that was given to it by the parent. So here, these two child threads are exploring what if we have this constituent of 53 minus 22 or 53 minus 31 in our arithmetic expression? What if we know we have that? How could we keep doing some reasoning to find a successful arithmetic expression? So here, child number 2 did find an expression that leads us to the correct target number. And what it'll do then is it'll join back to the parent thread. And when the child thread is joining back, another very critical thing is it's not going to return its entire reasoning chain. It doesn't have to return the things it explored that were unsuccessful. It just returns the successful part of it, and then the parent thread is going to synthesize these child results. So it knows that the first child didn't find a solution, but the second child did, and the expression that it provided was this one that gives us the target number, and so then it's going to say that's my answer. My child number 2 gave me the answer. It's successful. I verified it. That's my answer. Okay, so that was sort of the architecture of our model. How do we actually train it? So first we use the supervised initialization of the policy by sampling demonstrations from symbolic search. So this is following stream of search. We have some kind of search algorithm that gives us successful arithmetic expressions and also tells us how it got those, but it's not optimal. So it might include a lot of samples of like suboptimal incorrect attempts. And what's powerful about this is not that it's teaching it, the best way to do the search. It's just teaching it the general structure of calling fork and join. So if it has, an arithmetic expression already, then maybe it could fork to generate some kind of subprocess search.
Hello,
Now the
Alane.
key part happens when we have,
Hello.
oh, sorry.
Yes, sorry. Sorry to interrupt. Given the time, so how long do you think you'll finish? We want
I
to
have
save
maybe
some
like
time for.
just 2 minutes. Yeah.
Okay, great. We'll have questions afterwards. Okay,
Yeah.
great.
Cool. So the next key part is that we're using reinforcement learning to optimize the structures that we're actually searching over. So what we find when we do this is we maximize the parallelization. And basically the reward here is just like 1 if the search result that we sample from our model is a successful arithmetic expression. Okay, so a couple of results that I will go through quickly. First, we find that APR in orange, compared to the serial approaches of stream of search, gets us significantly higher accuracy with the same amount of context. And to achieve the same accuracy as stream of search, we need like less than half the compute. And this is because we can parallelize the approach and the actual inference threads we're running aren't operating on the entire context. The other key outcome result here is that if we look at the latency, the real-time latency in inference, we get significantly improved latency for the same accuracies. Okay, so just to summarize this part, we propose models distribute their inference time compute across serial and parallel operations. This improves both efficiency and accuracy over serialized methods. We can use exploration-based learning to discover optimal inference structures. And then finally, in future work, we're really interested in applying this to agentic tasks like software engineering, more complex math reasoning tasks, and there's other sorts of things like transparency and interpretability. Okay, so we can't train agents by scraping the web for demonstrations. We can use off-policy demonstrations. This leads to error propagation. So instead, we should train on policy using environments that let us execute actions. We can train with humans in the loop. We can use automated verifiers. And we can structure inference hierarchically to get better reasoning structures and more efficient inference. Okay, so thank you to everyone, my collaborators, and also for everyone for listening. I've underlined Jia Pan, who's the lead student author on a lot of the work that I proposed. So yeah, thank you. I'm happy to take questions.
Okay, great, great. Yes, thank you, Alane, for the wonderful talk. You covered three very important and interesting topics on agent for sequential instruction following, automatic evaluation, and also the parallelized reasoning. That is very interesting. So let's see if so we have 5 minutes for questions. So audience, please feel free to unmute yourself to ask any questions. So actually, I have so I will take one to ask the first question. So actually, I have a question about the second part on the automatic evaluation. Um, my question is that what is the main motivation for creating in the domain general automatic evaluation, and and how do you adapt to new tasks or new types of agents with the automatic evaluator?
Yeah, so I mean, in the work I proposed, I talked about our evaluators are domain specific. So we have evaluators trained for device control, we have evaluators trained for software engineering, but they're domain specific evaluators. So the main sort of generalization that they have to do is both to new agents. So we have a new agent that, is going to have a different policy than what the evaluator was trained on, right? And so the evaluator still should be able to give good evaluations of that agent. And the other form of generalization that they have to do is on new tasks. So new task specifications. And so in our work, we were evaluating our agents both, our evaluators both on different agents and also on different tasks that are held out from the evaluator training. Does that answer the question?
Mhm. Yes, and actually, I have a follow-up question on this. Is so basically, the evaluator is constructed based on the trajectory of the agent's behavior, right? And so in that so in this way, so how could you make sure that the trajectory of the behaviors are representative enough for the agent
Yeah, that's
policies
a
or
good
strategy?
question. Yeah, because when we're training an evaluator, we are sampling from a particular agent. It's only trained on the trajectories from a particular agent. Um, so I mean, I think maybe we didn't look into this. I think it's an interesting question of like what do you need to make the evaluators more agent general? I would imagine that training on like if you sample with higher entropy, so if you sample with higher temperature, sample more random trajectories, you are going to be exposed to weirder spots, like weirder kinds of trajectories that you might not see until you come into like a random agent. So that's one option. We didn't look at this directly in our work, though.
Great, thank you. Any any more questions from the
Okay,
audience? Oh,
so I
sorry.
saw one in the chat. How is learning affected when the evaluator is incorrect? Yeah, that's a great question. So we did look at this for the inference time scaling, where we use the evaluators to do like re-ranking. And in practice, for something like reflection, it isn't, yeah, it's not great when the evaluator says something is wrong, but it's actually correct, because that sort of makes the model like just completely fail. There's no more opportunity for it to create a new attempt. So that is a problem. In terms of like learning from evaluators, yeah, it's also a good question. I think I agree with you that it would probably act more as a regularizer. I think these learning algorithms are like relatively robust to noise, so I don't think it's a huge problem. Cool.
Thank you.
Great. Yeah, thank you, everyone.
Great. Yes, and yes, we are almost at time. So maybe one last question that I'm personally interested. So what would be the next research project that will be mostly excited about?
Yeah, so I'm really excited about this like parallel inference task decomposition stuff, because I think that long chain of thought just doesn't make sense to me. We know that it doesn't correlate with actual reasoning. It's just sort of this weird latent space that looks like real language that ends up being useful as a scratch pad for reasoning. And it like kind of is interpretable, but really not. But I think we could do something much better, which is like we actually ground that in the underlying reasoning space for a particular problem. And I think there's just so many benefits. Like if we don't have to worry about the the context window limitations, if we do some kind of information decomposition, then some parts of the problem don't have to reason about tokens that are irrelevant to them. Whereas in long chain of thought, like if you think about the average, like if you sample two random tokens in a long chain of thought, they're going to be completely irrelevant. Model has to learn that there's irrelevancies, but if you do a decomposition, it doesn't have to learn that. And then you can do stuff in parallel too. So I'm really excited about that approach, and we're currently looking at like applications to tasks like math reasoning.
Yes. Yes, that's yes, interesting. And also it might be relevant to consider like a coordination across different
Yeah,
reasoning
it's also very relevant to
modules.
agentic tasks. Yeah, yeah.
Great. Yes. Hello. Unless you have anything to add, I think we are concluding the seminar today.
Yes, sounds good. Thanks a lot for the fantastic talk, Eileen. Really nice to have you all.
Great. Yeah, thank you so much for inviting me. And thanks
Yes.
everyone
Have a
for coming.
great Friday.
Thanks. You all too. Bye.
Thank
Bye.
you. Bye.